Okay, so we can get a lot of energy released from nuclear fission reactions. Where does the energy come from? Right? Energy has to come from somewhere. Well, here we have the reaction. Uranium-235 plus a neutron. We get barium-140, krypton-93, 3 neutrons. Let's look at mass conservation. So here is the mass of a uranium-235 nuclide. Notice it's very close to 235. Here we're being very, very precise. So this is 5 decimal places, right? And so we've got that and the mass of 1 neutron. That's the total mass of reactants, 236, blah, blah, blah. And then over here, we can add up the masses of all the things that are produced, and we get 2 to 35.9, essentially. This mass is a little smaller. Now, if this was an experiment that first-year chemistry students were doing, and you started with 236.1 and you got 235.9, we'd say, good job, right? Really awesome. That's really, really close. But look at the precision here. We're out in the 5th decimal place. There's variation in the ones place. This is a significant difference. Is it huge? No. But is it a real difference? Yes, it is. So where did that mass go? The mass was converted into energy. So in nuclear reactions, mass can be converted into energy. This is not true in other chemical reactions. Questions? So you've probably seen this equation before, E equals mc squared. This is Einstein's famous equation. The energy produced in this process is equal to the mass that's lost times the speed of light squared. So we can calculate the energy produced in the fission of uranium-235. So how do we do that? Well, we need to find the mass that has been lost. So we're going to go back to this slide. So that's the mass we started with, and we're going to subtract the mass that we end up with. 236.05, 258 minus 235.86769. 0.18489 atomic mass units. So that's the mass that has been lost. So mass is equal to this many atomic mass units. The speed of light is known more precisely than this, but this is close enough. 3.00 times 10 to the 8th meters per second. So if we use these units, we're going to end up with a mess, because we're going to have atomic mass units meters squared per second squared, which is not a unit of energy. So we've seen that like a joule is a coulomb per second. An amp is a coulomb per second. There's all these different relationships between the base units. A joule is equal to a kilogram meters squared per second squared. Because mass times a distance, so a kilogram meter is equal to a Newton, I believe, and that's a unit of force. Force times acceleration is energy, and acceleration is meters per second squared. So that's where this comes from. You're not going to be tested on that. So the question is, if this is for one nuclide, how would we figure out how much energy, say, for a given mass of reactant or something, right? Or, what if there were 10 nuclides that reacted? Well, this is the amount of energy for one nuclide. So you would multiply by the number of decay events. Well, not decay events, but radiation events. So if you were doing a mole of nuclides were reacting, then you'd multiply by Avogadro's number. Yeah, good question. Any other questions? So let's look at helium-4 nucleus. So we're just ignoring the electrons because numbers of electrons we're not looking at the electrons in the products or in the reactants, so we're just leaving those guys out. A helium nucleus has two protons, which are the same as a hydrogen, and 2 neutrons. That makes a helium nuclide. So the helium nuclide has a mass of 4.00260 atomic mass units. And we can calculate the mass of reactants that went into that, and that's 4.03298. So again, we see that there's a loss of mass. The mass of the nuclide is less than the sum of its parts. Does that seem wrong? It should seem wrong. It's like, wait, how does that happen? You put some fruit in a box, and the box weighs less than the fruit plus the box? What? That's not how things work. But it's how things work here on this quantum level. So this is called the mass defect. You can do this with any isotope, any nuclide. You can look at its mass and compare it to the mass of the parts that make up that thing, and there's going to be some missing mass, and that's called the mass defect. So the energy that corresponds to that mass defect is called the nuclear binding energy. So that's the amount of energy that would be needed to break apart the nucleus into its individual components. So take a helium nuclide and break it into 2 protons and 2 neutrons. That mass defect corresponds to the amount of energy needed to do that. So nuclear physicists often use electron volts to report energy instead of joules or something else. And so the unit electron volt is the kinetic energy of an electron that has been accelerated through a potential difference of 1 volt. So again, we're dealing with, metric units of volts and just defining things in different ways. So a mega electron volt is equal to 1.602 times 10 to the minus 13th joules. You don't need to memorize that. And so we can work out a conversion. 1 atomic mass unit is equal to 931.5 mega electron volts. Just, an interesting side note. In Chem 1A, there's a worksheet where you have to calculate the energy transitions in a hydrogen atom when electrons go to different levels. And I can always tell when somebody Googled the answer, because when you look that up on the internet, you find answers that have electron volts, because that's how nuclear physicists do it, but that's not how we were learning about it in Chem 1A. And so you get this person with this long written out explanation in electron volts, and I'm like, we haven't even mentioned electron volts. You have no idea what electron volts are, right? So 0 on that one. Now we know, so you can use them. So this is a very useful conversion factor between mass defect in atomic mass units and energy in mega electron volts. You don't need to memorize that, though. It'll be given if you need it. Okay, so the mass defect for helium-4 is 0.03038 atomic mass units. What's the nuclear binding energy? Well, we could do E equals mc squared, but we don't need to because we have that relationship now between atomic mass units, a mass unit, and an energy unit. So we can just do this as essentially dimensional analysis. 1 atomic mass unit equals 931.5 mega electron volts. So if our mass defect is 0.3038, we're just going to put this together so the units cancel out. 0.03038 times 931.5. Oops. That'll be 4 sig figs, 28.29897 mega electron volts. That's the binding energy that is holding together a helium-4 nucleus. If you wanted to smash it, break it up into its parts, you'd have to put this much energy in. So you're going to have different nuclear binding energies for different sizes of atoms. And so it's a little hard to compare because they're different sizes. So what we'll often do is we'll look at binding energy per nucleon. Remember what a nucleon is? It's a resident of the nucleus. Protons and neutrons are nucleons. So for helium-4, if we wanted to know the binding energy per nucleon, we're going to divide by the number of nucleons. How many nucleons in a helium-4? 4. So if we divide by 4 nucleons, and we're going to get 7.075 mega electron volts per nucleon. So you can look at the mega electron volts per nucleon for different elements, different isotopes, and if you have a larger binding energy per nucleon, that's going to be more stable. Any questions? Calculate the mass defect and nuclear binding energy per nucleon in mega electron volts for uranium-238, which has a mass of 238.05074 atomic mass units. We do not have all the information we need in this slide to do this problem. We need to know the mass of a proton and the mass of an electron. I'm sorry, neutron. Proton and neutron. So we're going to go back here. This is the mass of a proton. This is the mass of a neutron. So I'm going to stick those in my calculator because I know I can't remember them. Oops. Of course, I can't even type them in right now, so that's a different problem. Okay. So uranium-238, the mass number is 238. How many protons are there? 92. We find that from the periodic table. It's element number 92. So we have 92 protons, and the mass of a proton was 1.007 83 atomic mass units per proton. And then we can find the number of neutrons by subtracting here. 238 minus 92, 146 neutrons. And then we'll multiply by the mass of a neutron. So 92 this gives us 92.72036 atomic mass units. And this gives us 147.26436 atomic mass units. So we'll add those two masses together. $239.98472. So that's the mass of the pieces, right? The 92 protons, the 146 neutrons. We're told here in the problem that this nuclide has a mass of 238. So this is the actual mass. So after we calculate the mass of the parts, we're going to subtract the actual mass to find out what the mass defect is. $1.933936. I don't know why I can't write AMU today. Maybe because it's Monday. It's a good enough reason, isn't it? So that's our mass defect. We can just convert that to electron volts, mega electron volts. $1801.46. Wait, yeah, mega electron volts. Is that the answer? No, it's very close. It's asking for the energy per nucleon. There will be a question like this on the exam. It will probably ask for energy per nucleon. And the most common mistake students make is they forget to divide by the number of nucleons. And that wrong answer will probably be one of the choices too. So to find the number of mega electron volts per nucleon, we need to divide by what number? The number of nucleons, which is 238. Yeah. It is 92 plus 146. 238. Nucleons. Divide by 238. 7.569 mega electron volts per nucleon. Any questions? Remember what the binding energy per nucleon was for helium? It was 7.0 something. So which is more stable, uranium-238 or helium-4? Which has the larger binding energy per nucleon? Uranium-238 does. Okay. The binding energy is how much energy you would have to put in to blast it apart. So this would take more energy to blast apart than the helium nucleus. So there's trends in nuclear binding energy per nucleon. Here we're looking at the binding energy per nucleon as a function of mass number. The mass number is the number of nucleons. So it starts out very low. This is deuterium, an isotope of hydrogen. This is an isotope of helium. Here we've got regular helium, helium-4. And so we see that there's this increase and then a slow decrease. It's at a maximum at atomic or mass number 60. That's where the most stable ones are. So who's got a mass of 60? Right, so that's like cobalt, nickel, copper, those guys. So those are the most stable ones. If we break a heavy nucleus into lighter ones, that's an exothermic process. If we take two light nuclei and combine them into a heavier nucleus, that's also exothermic. And there's a typo there. That B shouldn't be